Hello everyone, this is lecture 7 of course PE 645. In today's lecture we are going to deal with local binary pattern or LBP. Local binary pattern is a texture descriptor used in image processing for feature extraction. It's based on the appearance features, and LBP can describe the local structure of an image in a way that's invariant to the changes in the illumination of the image. LBP was first introduced in 1996 by Ujala et al., and it's applied in various domains, including texture classification and object recognition. LBP is very simple and effective. That's why it can be a good choice for many computer vision tasks. Simply, LBP works by comparing the intensity of a central pixel in a small neighborhood with the intensity of its surrounding or neighboring pixels. Each pixel in the neighborhood is assigned to a binary value based whether its intensity is greater than or less than the intensity of the center pixel. So, for example, if the center pixel is 50 and the neighboring pixel is 60, so the neighbor is more than the center, then the new value or the new binary value will be 1. Otherwise, it will be 0. These binary values are then concatenated into a binary number, and this binary number will represent the texture of that neighborhood. By doing that on all of the pixels in the image, we can construct a histogram of the texture distribution within that image. So what are the different steps to calculate the local binary pattern? First, choose a pixel in the image and select its 3x3 neighborhood in a circular or rectangular region. So if you are selecting the pixel 40, the neighborhood will be 3x3 that surrounds that pixel, which will be that region. You can obtain that region whether you are using rectangular region or circular region. Also, LBP can be extended to 5x5, 7x7, or different sizes, but commonly 3x3 neighborhood is used. Another example, if you are selecting the pixel 28, then the neighborhood, if you are using circular fashion, it will be like that. So the neighborhood will be 40, 21, 11, 41, 12, 22, 13, and 10. After that, apply the thresholding, and the threshold value will be the intensity of the selected pixel in the center, which is in our case is 40. Then go through every neighboring pixel and check whether the intensity of that pixel is greater than or less than that threshold. For example, 21 is less than 40. If the intensity is less than the threshold, assign a binary value to the pixel to be 0. So 21 is less than 40, the assigned value will be 0. Moving to other pixels, 22 will be 0, 18 will be 0, 23 will be 0, 55 will be 1 because 55 is greater than 40, 41 is greater, that's why it's 1, 28 and 21 will be 0. After that, combine the binary values for all neighboring pixels to obtain a binary code. You need to determine the starting pixel and direction of movement. So for example, from the top left, and the movement will be counterclockwise or anti-clockwise. So the binary code will be 0, 0, 1, 1, 0, 0, 0, 0. And this is a binary code that represents the center pixel. Then you need to convert that binary code to a decimal value. That decimal value will replace the actual value of the center pixel. So to convert that value, you start from right to left and multiply each value by 2 raised to the power of the index. So 0 will be multiplied by 2 raised to 0, the other 0 will be 2 raised to 1, and so on until you reach 2 raised to the power of 7. Or simply, you can build another matrix like here, and based on the direction and the starting pixel, you start to put the 2 raised to the power of the index. So you start 2 by 0 and rotate anti-clockwise or counterclockwise until you reach 2 raised to the power of 7. Then you multiply pixel-wise, 0 multiplied by 2 raised to the power of 0, 0 multiplied by 2, 1 multiplied by 4, 1 multiplied by 8, and so on. You sum all of that numbers and the result will be 12. So the original 40 will be replaced by 12. Then you will need to repeat these steps for each pixel in the image. So for example, 18 here in the original image will be replaced by a certain value. This value can be obtained first by getting the binary code. So you need to build a neighborhood 3 by 3, and based on that threshold you need to set the binary code. These values are higher than 18, so the binary code for them will be 1. Other values 11 and 4 will be zeros because they are less than 18. So now you have the binary code. You multiply pixel-wise to the 2 raised to the power of the index and sum all of these numbers. You obtain 143. You replace then 18 by 143. You will loop on all of the pixels and obtain another matrix with the new values. Now you understand the technique, which is very easy, but how to do that programmatically? Back to GLCM and GLRLM, we got some equations that handle the position and get the target position based on the distance and theta, which is the angle. We can use the same equations so we can obtain the neighborhood that surrounds a certain pixel by simply assuming that the center pixel only got these surrounding pixels, which are 8, and the angle between each of them is 45, and the angle that we should start is the top left. As we mentioned in the example, it can differ, but when you are going to exchange the starting pixel, you need to apply the same for all pixels. So let's assume it's on the top left. So the starting angle will be 135, and to get the next angle for the next neighbor, we need to add 45 for each. So this one will be 180, and we do the same for each until we reach the last one. By obtaining theta, and the distance is 1 because they are neighbors with a distance of 1, each next to the other, we can obtain x and y. Based on x and y, we can obtain the pixel. So the formula will be x will equal to x center, and x center here is the location of the center pixel plus the round of distance multiplied by cosine theta. And y is similar, but instead of x will be y, and instead of cosine will be sine, and we are switching plus to negative. So for example, we start at 135 and we are moving counterclockwise. So how to obtain that location? We have the center pixel at 1 and 1, x and y. So 1 plus the round of cosine 135 will be 1 minus 1 will be 0. And for y, sine 135, the round of it will be 1. So 1 minus 1 will be 0 also. So the pixel location will be 0 and 0. We can also get the benefit of doing that by creating a counter that starts from 0 to 7 that will help also to create the kernel that will be multiplied by the neighborhood. As mentioned earlier, we need a kernel that should be multiplied by the binary code to obtain the final value. So by doing that, we can obtain the kernel. Because we are starting here, so the counter will start at 0. So the kernel at that value will be 2 raised to the power of 0, which will equal to 1. After that, we will get the next pixel by incrementing 135 by adding 45. So the result will be 180. By calculating x and y, we can obtain 0 and 1 as a location, and the counter will be incremented, so 2 raised to the power of 1 will be 2. By doing the same and looping on all of the kernel or the neighborhood, we can obtain the surrounding pixels and the kernel that should be multiplied by the binary number to obtain the final value. Another issue happens with the pixels on the boundaries. For example, 17 here is required to build a neighborhood 3 by 3, so there is no pixels here. So how to handle that? Simply, we will need to pad the image by adding zeros around the image. So this will help to get a neighborhood for the boundary pixels. For example, here will be that neighborhood, and here will be that neighborhood, and the same for other boundary pixels. And we are padding with zeros because 0 multiplied by any number will be 0. So by doing that, the values will not be affected. To do that using the code, we imported the NumPy package and created the matrix in our example and converted it to a NumPy array. Then we defined the distance, which should be 1, and defined if we need to move counterclockwise or clockwise, and based on that the final values and the features will be different. And the original theta will be 135, that will start from the top left corner. Then we obtained the center X location and center Y location by simply multiplying the distance by 2 and adding 1. In that case will be 3 as the window size, and the center X and center Y will be 1s. Doing that will help if we have different distances. For example, at a distance 2, the window size will be 5, and the center location will be 2 and 2, and so on. Then the LBP matrix will be similar to the original matrix shape, so we created LBP matrix with 0 values, and a kernel with a size of 3 by 3 in our example, because its value in this case will be 3. After that, we padded the image with a constant value of 0, and this will pad the image boundaries, top left, bottom right. Then we started to fill the kernel based on the angles, starting from 135 and adding 45 for each iteration in the loop, as we discussed here. So simply we need to loop on all of the kernel, which is sized window size and window size, width and height. So the length of it will be window size raised to the power of 2. So we are looping from 0 to the end of window size to the power of 2. And you are subtracting 1 from here because the center pixel will be ignored. So now instead of getting 9, we need only 8. After that, we get the X location and Y location using the formulas, the distance multiplied by cosine and distance multiplied by sine for X and Y respectively, and adding center X, and here we are subtracting from center Y. By getting X and Y location, we can now update the kernel value to 2 raised to the power of I. I here is the counter that starts from 0 to 7, because the last value in the range is not included, which is 8. So it will start from 0 to 7. Then it will increment theta based off we need to go clockwise or counterclockwise. So if you need to go clockwise, we need to subtract 45. And if we need to go counterclockwise, we need to add 45. So based on that, we will obtain the kernel, which will be that kernel. But instead of filling it manually, we got it programmatically. This approach will help also if we got different distances. Then we need to loop on all of the pixels in the image, get the region, convert it to binary, and multiply that binary code by the kernel, and then sum all of the numbers and set it to the LBP matrix. So here we are looping on Y and X. Then we got the region from the padded matrix. Then we compared that region to the center pixel of that region. It will be 1 if higher or equal, and will be 0 otherwise. So the comp variable will contain a binary code in the form of a matrix. You can multiply comp by the kernel or simply access the kernel with the comp. What does it mean? The multiplication between the kernel and comp is illustrated here. We have comp and the kernel multiplied together pixel-wise and sum to get a final value. What about accessing kernel of comp, which is here? As you know, these values are binary. So if we accessed only the elements in the kernel, which is here, with the values of ones, we can also obtain the same result. So simply, if this matrix contains zeros and ones, and if we apply indexing to a specific matrix with zeros and ones, it will return only the elements at the ones. So in that case, it will return only these values. By summing these values, we can obtain the same result. So whether you do that line or that line, you can obtain the same result. Finally, we printed the original matrix and LBP matrix, and this is the corresponding result. By setting theta to 135 and changing only clockwise and counterclockwise, we obtain two different LBP matrices, as shown here and here. LBP has different pros and cons. Some of the advantages of LBP: it's robust to illumination variation, as it captures the texture information in the image with varying lighting conditions. It's suitable for large datasets and real-time applications. It's invariant to rotation and scale, and it's highly discriminative. And some of the disadvantages of LBP: it's sensitive to the noise, which may lead to inaccurate binary values and LBP histograms. It's limited to local texture information, as it misses the global texture information in the image. However, it's rotational invariant. It doesn't differentiate between textures that differ in rotational patterns. And finally, it's applied to grayscale images. So if you have a colored image, you need to convert it first to grayscale. So how to apply the local binary pattern on a dataset or a 2D image? As noted earlier, we have image and the corresponding mask, and we need to get the ROI and the cropped ROI. We can simply replace the matrix with the image. And that's what we did here. We encapsulated the local binary pattern into a function, and inside that function, we built the same thing and finally returned the LBP matrix. Then we added the portion that loads the image and gets the ROI and the cropped version. Then we called the function by passing the cropped image theta and is clockwise or counterclockwise. Then we got the LBP matrix. From a while, we mentioned that from the LBP we can obtain a histogram. So simply we can build the histogram as we did with the first order features. We get the minimum and maximum boundaries and count the number of occurrences for each pixel. And then we can visualize it and visualize LBP matrix and the cropped version. Also, we can obtain different features from the histogram, such as the percentile. Here we defined 5 quantiles from 10 to 90 and printed that. When we execute the code, we can obtain these results. These are the percentiles, which also can be features. We have 5 values, so we have 5 features for that image. And this is the corresponding histograms, but in our visualization we omitted the 0 and 255. And this is the LBP matrix, which visually can be a texture descriptor for some tasks. But the question now is, the percentile is the only feature that can be extracted from the histogram? Of course not. By obtaining the LBP matrix, we can consider that as a new image that can be applied to any of the mentioned features, such as first order, GLCM, and GLRLM. So instead of working with the original image, now we can work with the LBP image. For example, we can combine between the LBP and GLCM, and calculating the GLCM from the original image or from the local binary pattern involves distinct methodologies that capture different aspects of texture and spatial relationships with the image. If we are focusing to compute the GLCM with the original grayscale, we are focusing on the statistical dependencies between the pairs of the pixels based on the different intensity values. So the features that are obtained from the GLCM with the original image will provide insights into texture characteristics such as intensity variations, uniformity, and structural complexity. While GLCM obtained from LBP image will operate on a transformed representation where the image is first converted into a binary pattern matrix using LBP, and this transformation will emphasize the local texture variation rather than the absolute pixel intensities, which in somehow will be less sensitive to the illumination changes and noise. In that case, we are focusing on features like uniformity, edge responses, and rotational invariance from the LBP matrix. Also, we can combine both of them. We can obtain features from the grayscale image and features from the LBP matrix and combine that in our file to work together in the classification model. And it's not limited only to GLCM. As mentioned, you can apply all of the mentioned techniques on the LBP matrix, considering it as a new image or as a new matrix. So in that code, we combined the local binary pattern function, GLCM and GLCM features functions together, loaded the image, applied the bitwise to get the ROI and the cropped version, and then we defined the distance and theta for GLCM and postfixed it with GLCM keyword, and also defined theta for LBP. Then to compare between both of them, we first calculated the GLCM features for the cropped image and stored that in the features variable. Then we calculated the GLCM features from the LBP image by first calculating the LBP matrix and applying the GLCM functions on the LBP matrix. But it's worth noting that we subtracted 255 from the matrix to convert the background from white to black, because in that function we are setting to ignore the zeros. So to make a match between the matrix and the function, we applied that line. Finally, we printed the features for the cropped and LBP alongside each other, each in a line, and by executing the code we obtained these results. This for the GLCM features applied on the cropped version, and this for the GLCM features applied on the LBP matrix. For example, the contrast, there is a small value compared to that value in the LBP version, which can underscore that the LBP can emphasize sharp transitions and local variations in the texture, which can reflect its sensitivity to finer details in image patterns. But setting both together in our feature file that will be provided to the classification model may help to improve the performance. Moreover, talking about the dissimilarity, it's higher in the LBP image than the cropped image, which can reflect that the LBP can detect the differences between the adjacent pixel intensities and can reflect its sensitivity to subtle variations in the texture patterns. So by returning to the definitions for each of these features, we can understand the differences between the results of the cropped and LBP versions. There are different variations and extensions for the local binary pattern. One of them is the uniform local binary pattern. Uniform LBP or ULBP considers only the patterns that have at most two transitions from 0 to 1 or 1 to 0 in the binary code. So the ULBP will categorize the binary patterns as uniform or non-uniform based on the number of bitwise transitions, as mentioned 0 to 1 or 1 to 0. And we can say that a pattern is uniform if it contains at most two bitwise transitions, which means 0 or 1 or 2 transitions. but higher than that, it will be non-uniform. By doing that, LBP will address the issue of high dimensionality of LBP histograms by focusing only on patterns that exhibit uniformity. And this will also reduce the number of possible distinct patterns, which can help the LBP to be more robust to noise. So to apply that, we simply get the LBP matrix and create another matrix called uniform matrix, and then we will loop on the LBP matrix and check whether it's uniform or non-uniform. If it's uniform, we will consider that value. If it's not, we will set it to 0. So that matrix contains decimals or integer values, and we need to get the corresponding binary code of each value. So simply there is a function called binary representation that accepts a specific value and converts it to a binary code, and then we loop on each element in that code and count the number of transitions. To count the number of transitions, we check the current pixel and the next pixel. If they are the same, then this means there is no transition. If they differ, then there is a transition. That's why we are checking the current value with the previous value. If they are not the same, increment the number of transitions. At the end, if the transitions is less than or equal to, convert that binary code to an integer value, or we can use that value again. So instead of using that line, we can use the old value. Both of them will be similar. Finally, we return the uniform matrix. So the uniform matrix will be a reduced version of the LBP matrix, because some of the values will be ignored and set to 0, and these values, which will be set to zeros, will reflect that there are more than 2 transitions. We encapsulated that in a function called uniform local binary pattern and executed it here, and executed the old version to compare both of them together. The first is LBP matrix and the second is postfixed with the keyword uniform, and then plotted both together. When the code is executed, we got the uniform and the traditional or the original version. As you see, there are many darker regions here because some pixels are set to 0. And as mentioned, we can use the uniform local binary pattern image as a matrix that can be applied to any other features such as first order or GLCM. So in this lecture, we discussed what is the meaning of local binary pattern, how to calculate the local binary pattern using a set of steps by initially getting the neighborhood, comparing between the center pixel or the threshold and the neighbors, computing the binary code and sum all of the values as a decimal value, and setting it to the new matrix. And this is applied to all of the pixels, and we solved the issue of the boundary pixels by applying padding to the image. Then we applied histogram to the local binary matrix, and based on that histogram we can calculate features such as first order features or other features that depend on the histogram, such as percentiles. Second, we can use the LBP matrix as seen with other features such as GLCM. Then we dealt with an extension of the LBP extensions, which is called uniform LBP, that only considers the values with at most 2 transitions and ignore others, and that version will be more robust than the original one to the noise and will decrease the dimensionality of the histogram.